Log on, tune in, find out. Another good idea from Cambridge.
You fix the f for a fixed f. But the question of recovering both is not known. It's a very interesting problem. Okay. It's a good question, thank you. Okay. So let me recap very quickly. So this is just the first step in photoacoustics. We're solving a wave equation problem, and then we're going to solve an elliptic problem, but with data in the interior. This is a boundary value problem. So we have the wave equation. We have the wave equation and some initial condition that came from a source. But you can reduce the problem to initial condition, and we make the measurements of the solution, the pressure outside on the boundary across time. And the inverse problem is, can we recover the source? This is a physically corresponds to the amount of thermal deposit thermal energy from these measurements. Okay, so what we propose is a modified type of time reversal. So we're going to use the fact that the solution is invariant and the change is t to minus t, and we're going to try to reverse time, but we're not going to solve the problem like in a standard time reversal with data 0 for capital T sufficiently large. Instead, we're going to give data phi, where phi is a harmonic function with boundary condition, the value of the data on the boundary, so that these are compatible. And the reason to choose this phi in such a way was in order for this to minimize energy among all the possible solutions that have the value h at the boundary, because the energy is given by this and this is 0. So you're trying to minimize this for all use with certain boundary value, and the solution of that is a standard Laplacian, the solution of this elliptic boundary value problem. So that's the idea. Okay, so when you apply this is the data, you apply the modified reversal operator, which is A. So I should have written it down here. B at 0. When you apply this operator to the data, you get back F. So it's an inverse, but you get an error. And the error is given by the value of W, the solution of this problem, at 0. So this is the same wave equation. So this is K of F, W of 0, solution of the same wave equation with data, the same data as U there. And the initial velocity at time capital T, the same as U, and with Dirichlet boundary condition. Okay, so what the goal is to prove that the norm of K as an operator, as a boundary operator from H1 to H1 is strictly less than 1 for T sufficiently large. And in fact, I'm going to prove it for T1, where this is the supremum of the length of geodesics on omega closure. This is not the sharpest result, but the one we can prove with the technology that we have now. So let me, yesterday we proved that norm of k, when it's clear the norm, I'm not going to have subscripts, is less or equal than the norm of f. And these follow from the following string of inequalities. So it's less or equal than the energy of the solution at time 0, because the energy contains the data. Remember, k of f is w at 0, contains the L2 norm of the data, the gradient, the L2 norm of the gradient. And this, by conservation of energy, is the same as this. And we proved yesterday that this is less or equal than the energy for U, for the U that is on the left blackboard, a star, and this is less or equal than E of Rn, U at T. Yeah, we proved that the energy was decaying, and this is less or equal, I mean, this energy is less or equal than that. This is clear. This is, by conservation of energy, this is the same at the energy at 0. And this is exactly the H1 norm of f, just measuring the gradient of f squared. So this is what we did yesterday. And now today I want to prove, first of all, the norm kf is strictly less than f. F is non-zero. Okay, so assume the opposite. So how many people did the homework, by the way? How many? Well, if you raise your hand and you have to come up here, I bet nobody will. So assume not. So all of these strings of inequalities are equalities. You have this on the right-hand side and kf on the right-hand side. So assume not, so norm of kf is equal to f for f non-zero. So in particular, you have that the energy on omega of u is the same as the energy in Rn of u. So that means that the solution u has to vanish outside omega for time t. Right? And now, by finite speed of propagation, this was one of the properties that I mentioned yesterday of the wave equation. This implies that u of xt is 0 for distance of x to omega bigger than t minus t. So if the solution is 0, vanishes outside some set, then it will be 0 for larger times determined by the light cones starting at the different points of the support. Okay? But we also know that u, but we also know that the f is supported in omega. So we can conclude using the same finite propagation speed that this is true. Okay? So from these two, you can conclude, it's a small exercise, that u is 0 is that the distance from x to the boundary of x, omega is 1/2 bigger than 1/2 t, for t bigger minus 1/2 t minus 1/2 t less or equal than 3/2 t. This is just a small calculation. I don't have much time, so I cannot do all the details. So for an interval of time, the solution is 0. So this is the situation. So let me draw the picture here. I'm only going to use, here is where I want to use Tataru's unique continuation result. So here I'm going to draw x. So here is omega, and here is the distance here is 3/2 t. So let me put minus r for simplicity, and r plus 1/2 t. So the distance from here to the domain is bigger than 1/2 t. Okay, so you know that the solution is 0 for this amount of time. Oh, by the way, since you can reverse time, t to minus t, you have that this is equal to 0 for t less or equal than 3/2 t. So you can go all the way to minus 3/2 t. Okay, so the solution is 0 from here on. And this is a time-like surface, and now we apply a unique continuation, Tataru's unique continuation result, to conclude that u will be 0. Of course, it's 0 on the other side. In this diamond type figure, I'm only taking this side here, and also from the other side. And you can see this is another small exercise that this will fill the whole region. Unfortunately, I don't have enough. I wanted to leave the formulas there. So this implies that u is in fact 0 on omega cross omega. And this is a contradiction because, of course, that implies that f is 0, and we were assuming that f is non-zero. Okay, so we conclude this is a. I mean, I didn't do all the picture to do this correctly. I had to do a good picture, and I cannot in the blackboard. So this is a small exercise. But the main tool is by Tataru's theorem. Okay, so we have the norm of Kf is strictly less than norm of f, if f is non-zero. Right? Okay, now I want to prove that the norm of k is strictly less than 1. Is this enough to guarantee that? No, right? It's not enough, because you can have sequences that get closer and closer to this. So, by the way, for all of these arguments, I only use the fact that t is bigger than t0. T0, remember, was the diameter of omega in this metric. Right? I didn't use anything more. T was slightly bigger. T is slightly bigger than the diameter of omega. But here is where I'm going to use another property of solutions of wave equations, which is different than elliptic equations. So what is number this? I said A was time reversal, t to minus t. B was help me here, conservation of energy. 3 was finite speed of propagation. 4 was Tataro's theorem. We have used all of those. And 5 is propagation of singularities. Okay, so hopefully, even though you may not follow all the details, at least you will see how the different properties of the wave equation come into play in this proof. So what does it mean, propagation of singularities? So I want to see, I have some singularities in the initial data here at time 0, how they propagate, where do they go? Of f, the initial data, how do they propagate? Okay, and there is a very deep theorem of Uhlmann that tells you how the singularities propagate. So this is the next for equations of this type. It's much more general than just the wave equation, but this requires more precise knowledge of singularities that I don't have time to describe, which is the wavefront set of a distribution. So I'm only going to give and we use this result in our paper, but I'm going to get a not so sharp result as a consequence. And so let me tell you the corollary of that theorem. So this is what I mentioned in the first talk. Singularities propagate along geodesics. So here you have your data at time equal to 0. Here are the supports, say, of f. You take functions, the places where the function is non-zero, and you have singularities here somewhere. The singularities will propagate along geodesics. So the answer is that's the reason why I define geodesics. And here the metric, remember, is 1 over c squared of dx squared. And I defined geodesics last time. I'm not going to define it again. So singularities of solutions of the wave equation propagate along geodesics, and the notion of wavefront set tells you not only the points where propagates, the direction of propagation. So you take a geodesic with a certain direction, it propagates along the geodesic. So as a consequence, we have the following corollary of Uhlmann's theorem. You want to know the singular support of the solution U. U is as in the left. For a fixed time t, okay. So singular support is all the points where the distribution is not smooth. It's contained in the y's. So the y can be joined by a geodesic to the initial data, to a point x in the support of f. As I said, it's more, but after time. So this is the time. after time plus or minus t. Okay, so you travel time t or minus t, and then the singularity will be, you started with something here, the singularity will be here. So, and t, the time this time corresponds to the length of the geodesics, because you can parameterize geodesics by arc length. So time is distance. So this t corresponds to the length of the geodesic. The theorem is much sharper than this and much more precise, but I don't have time to say it, but this is enough for what I'm going to say. Okay, so the singularities start here, they propagate. They don't stay like in the case of elliptic equations. You have a boundary value problem, you have a singularity on the border, in the boundary, it's an h1/2 or whatever you want, then the solution inside is immediately smooth, doesn't propagate anywhere. And that's a main difference between elliptic and hyperbolic equation. Here, you take a singularity, it propagates along geodesics. So as a consequence of that, now I can erase this. As a consequence of that, we have that for time sufficiently large. Remember, there was a time that we singled out before. Anybody? So this is one question in the test. What's this capital T1? There were many times, right? What is the relevant time here after the geodesics leave the whole domain? Right? So this is the maximum of the length of geodesics on omega closure. Right? That's the time. There were two times. One is the diameter. We use it already. And this is the other time is the supremum of the length of geodesics. And for this time, what happens? All the singularities have left, right? The domain. So there are no singularities on omega closure, because the maximum, you are taking the time sufficiently large so that this point has moved away from the domain. The time is large. Remember, the time corresponds to the length of the geodesic. So what does this imply? This implies that this map is smoothing. And also to UT. Right? No matter what singularities you have on F, the solution is smooth. So this is smoothing as long as T is sufficiently large and bigger than this time, right? So it's a smooth map. If it is a smooth map, a smoothing map, what properties does it have? A map with a C infinity kernel, I shouldn't call it K, G, has a kernel. Well, Adrian is using G for Green's kernel. This is not a Green's kernel. You have every bounded operator has a Schwarz kernel, and this will be a smooth. Right? No matter what singularity you have here, this is smooth, so this is smooth. And what can you say about G? This is a bounded domain. G is a compact operator. Right? G is compact. Okay, so this operator is compact, but remember the W that we have here is the initial, the K is the initial. I want to prove that the operator K is compact for T sufficiently large. So we have the map F to ut, so ut. And that's a smoothing, that's a compact map, right? This is compact. I just check at time t, capital T. This is a compact map, right? What can we say about the map to the pair? This is a compact map to the space of energy. How about this map to 0? This is compact. Another, before I do that, for the W, which is up there, not only I have u at t equal to capital T, but I have minus phi here, right? Remember, I want to check that this map sending f to W at 0 is compact. So I have to subtract the phi. But what can I say about the phi also in terms of f? But the data for the phi, and I just erase it, of course that has to happen. The data for the phi is smooth because the solution u is smooth on the boundary, smooth in the whole omega closure. So phi by elliptic regularity is also smooth. So you also have that this map is smoothing. Right? Because by elliptic regularity, Laplacian phi is equal to 0, and phi at the boundary is given by something smooth. No, because it's the solution u, remember, a capital T. And we know that that's smooth for t sufficiently large. Okay, now I apply another map here. I map this to 0. And the initial velocity at 0. What can I say about this map? W is the solution of that equation, right? This is the initial data, this is the initial velocity, and I map it to the data at time 0. What can you say about this? Another test. What can you say about this operator? It is conservation of energy, right? The W conserves energy because you have a Dirichlet condition on the boundary for W. So this is bounded, not more than bounded, it's a unitary map. But the only thing I need is bounded. Right? This is a bounded map. And now then you project to W0, and that's another bounded map. This is just the projection. So you have that the map from F to W0, which is K of F, is a composition of a compact operator and a bounded map, so therefore it's compact. So it's a composition of compact plus bounded. So this is compact. So therefore K is compact. Right? So now you are in good position. If you have, this is a fact from functional analysis, very easy to check, that if K is compact and so you have, now we can, there is this, we have already used it. And suppose K is compact, then this implies norm of K as a bounded operator from H1 to H1 is strictly less than 1. So these two facts imply that the norm is strictly less than 1. Okay. And so that's the end of the sketch of the proof. I didn't do all the details, but I hope I give you an idea. And the main interesting thing perhaps is the methods. You use a lot of the properties of the wave equation. Time reversal, Tataro's unique continuation result, of course, conservation of energy or decay of energy, depending on the situation, and propagation of singularities. Okay, so now I'm going to continue with this. Finish more or less the smooth case. Screen down. You can see all my secrets here. Oh, but the duplicate didn't work. I cannot see it otherwise in the screen here. Okay, so this is that was the case of C smooth. So by the way, the reference for this paper, they are all these what I'm going to discuss is on my web page. This is in a paper with Plum and Stefano, and it's in Inverse Problems 2009. Okay, so we were at a meeting last year at Banff, and Li-Hong Wang, who has been, as I said, the first lecture, one of the main proponents of photoacoustics and thermoacoustic tomography, proposed to consider the case of a brain. Very interested to do this on the brain, of course, but one of the problems is the effects of the skull for penetration of waves. And from our point of view, this is not working. So let me use this. So you have the skull here. This is the boundary, and you're making the measurements here, right? And so you have this part of the brain that has a very different speed than the speed of the rest of the brain, by a factor of 2. And here, so the question is, what happens in this case? Now, one of the main issues that in the proof I just gave was propagation of singularities. How singularities that start here propagate in that case, because you have this continuous sound speed. And the situation is quite different on the than in the case of smooth speeds, and smooth speeds just propagate along geodesics. So that's what happens here. So you start at the point with certain direction, you start your geodesic, but it can reflect, and it can keep reflecting depending on the degree of the angle that you hit this boundary of the skull. But in most cases, it splits into 2 rays. One reflects and the other refracts. And the same thing here, one reflects and the other refracts. So for a lot of rays, the energy that you get here is much less than the original energy that you started the ray here. So this is a complication. And the other complication, a more serious one, is that there are rays that stay here forever. So there are trap rays that are part of the geometry necessarily. Necessarily, you may have trap rays here. These are called rays of internal reflection. So what to do in that case? Well, of course, we cannot do anything. You have the support of your function here. We won't be able to do anything unless the rays get out somehow, right? We're making the measurements here. There is nothing we can do otherwise. So we're going to assume that you have a function f here is such that the rays, even though they may be broken many times, they arrive at the boundary. In that case, you can get a good reconstruction. So as I said here, propagation of singularities is the key, and trapped singularities are the problem. So you take a compact set and assume that the rays starting on that compact set leave the domain. And then we'll again have a Neumann series argument that recovers the F. So now the difference with this is that the C is discontinuous. In terms of the problem you need to solve, at the boundaries of the discontinuities, you solve the transmission problem across here and a transmission problem across here. Okay, so this is just a projection. This operator is a projection to guarantee that, because I'm assuming that the support is in such a place that all the geodesics starting here leave eventually. Okay, so you just take a projection from the energy space, this is, remember, H1, to this compact set. And in this case, you still have a Neumann series. So except for this, that is unavoidable, you cannot do better than that. If the rays don't leave, then you have the identity minus compact, and the norm of this is less than 1 for t sufficiently large. And the time t is also the same as the largest of the lengths of geodesics with respect to the same metric, but now the metric is singular, so you may have broken rays. Okay, so the procedure works. So let me show you some pictures. So this is in 2 dimensions, and here the speed jumps as a factor of 2. This is the case of the skull. This is the sound speed, and remember there were the zebras that have a lot of textures. This is the original. The pictures here in my computer are better than the ones you see here. This is 2 times the diameter, and this is the error. This is a Neumann series, and you take larger time, the error reduces, and so on. The time reversal, the standard time reversal method, which was asked to take it time equal to 0 for t sufficiently large, this is the original. This is as before 2 times, and you have a huge error. And here for 4 times you have another error, and here for 8 you can barely see anything. And the reason is the following, that time reversal does not take into account, you reverse time, and since the speed is discontinuous, you are going to create more reflections. So here you are, you start here, now you propagate back, but the rays that come here will reflect themselves, because you have a discontinuous speed. So you're going to create a spurious reflections that don't exist really on the original problem. That's why the pictures that you will think that they will get better for large time with time reversal, that's certainly the case for a smooth C, is not the case when you have a discontinuous sound speed. So this is a comparison of the original versus the Neumann series. This is Neumann series, and this is the error for 8 times the diameter of the domain. Okay, so we'll finish with this, and then I will continue with partial data. And the second part we have neglected at the moment. I have talked about the wave equation. The second part of the photoacoustics, remember you had to solve 2 problems, 2 inverse problems. One is a boundary value problem for the wave equation, and the second one is an inverse problem for an elliptic equation, but with internal measurements. And both of them are well posed. That's the main difference with the case of Calderon's problem that Adrian is talking about.